Thank you very much. Good night, everybody. Good night. Oh. All right, so my name is Yushu. I work for NERSC. NERSC, if you don't know what NERSC is part of Lawrence Berkeley National Lab. So if you don't know what Lawrence Berkeley National Lab is, then I can't help you. But it's their fault, not yours. What is NERSC? So NERSC is a DOE, Department of Energy funded computing facility where we have several petaflops on the floor. We're getting 30 petaflop. That's another issue. So we welcome scientists from around the world, thousands and thousands of users, to use our computers to compute whatever they want to do, hopefully related to science, right? And we are a production facility. We let user come in and use it. So, and we are funded primarily by DOE. So let's go through some of the less interesting stuff first. So this is the pie chart of what kind of code are running on our machines. You see most of them are like fusion energy, lattice QCD, climate, molecular dynamics. This may be one of the interesting ones. So we are, if you say traditional HPC, we are traditional HPC, if you know what it is. Right? And so this is who pays us, not pays us, but who seems like they're paying us. So these are the different offices inside. So there's Department of Energy, that's Steve Chu, used to be Steve Chu. And then there's Under Secretary for Science, there's the Office of Science. And then under the Office of Science, there are 6 offices for different science areas. One of them is Base Energy Science. They are our biggest sponsor. And there's also fusion energy, high energy physics, nuclear physics, advanced computing research center. Oh yeah, right. So blah, blah, blah. So by the way, if you don't know yet, DOE is actually the largest funder of fundamental science in US, maybe in the world, bigger than NSF. Right. So this is pretty much us, or this was pretty much us. So in the past 10 years, actually, because one of our primary focus today is to talk about big data and HPC, right? I hope that's within your vision. So in the past 10 years, the DOE facilities has been filled with more and more data, basically. So it's actually earlier than what the industry has felt it, just to remind you. So, so other DOE facilities say, we are a facility, we allow users to come in, but there are also other facilities funded by DOE, say the big telescopes, or the sequencing centers, or the light sources where they have a little proton running around and shooting X-rays to random people, right? So they are all producing more and more data in the past 10, 15 years. And they have been they have been traditionally running their computing, either simulation or data analytics on data centers like NERSC. So they have, so we have been working together in the past many years trying to figure out how to best handle data when your data grows. So we have a history in doing that. Just to give you a proof, so this plot shows this is terabytes per day. This is year. So how many terabytes are going in and out of NERSC every day from 2002? So we have 1 terabyte in. So the red one is going in, blue one is going out. So 1 terabyte in 2002, and now we have about 100 terabyte. It's growing pretty much exponentially. We may hit the petaflop day sometime in 2020. So 1 petaflop in and out. I mean, 1 petaflop in and 1 petaflop out. Oh, sorry. Yeah, right. So I'm still stuck in the traditional HPC era. So everything is a flop. So petabyte, 1 petabyte going in and 1 petabyte going out every day. So, and you can notice that we have consistently more inbound data than outbound data. So this is one signature of NERSC as well. So we are becoming a huge database after so many years of accumulation. We have over a petabyte of tape storage now, and it's growing like multiple petabytes per month. So, and these are some of the science discovery that we helped to make. So the first one, of course, everybody knows about the Higgs. Anybody don't know about Higgs? All right. If you don't know, so I have to rant a little bit because so I was involved in this project when I was a particle physicist, and I wrote the data analytics framework for the ATLAS experiment so that the scientists could run their implement their ideas to go through the petabytes of data so that they could find Higgs. So I have to credit myself for that. So and so if you know Higgs boson, so there's a thing called standard model of the universe, right? So that's basically the theory that's supposed to describe the whole universe. And the Higgs boson is the last unidentified particle or undiscovered particle in the standard model. And there's another thing called theta 1,3, which is the last unmeasured parameter in the standard model. And we were part of measuring that as well. So there's an experiment in China somewhere, has been streaming data from China across the Pacific to NERSC for the past 5 years or so. That's terabytes per day. And they successfully measured that number. Oh, wow. OK, good science. And another interesting thing we did, this is called the polymer transient factory, which is supposed to be looking for supernova or supernovae explosions. So this is a small telescope somewhere near Pasadena or near LA area. And what they do is that they take a lot of pictures of the sky every night and send it to NERSC, and it's automatically processed in NERSC. And the next morning, the scientists will receive an email, say, hey, I think I found a supernova. Have a look, right? So this is how they found the youngest and closest type 1a supernova in the past 40 years. So maybe 10 hours after it exploded. So if you think the astronomical scale, right? Things are many light years away. You discover something 10 hours after it happened. That's significant. So, and a good thing about this is a very small telescope. And all the super expensive telescopes around the world sort of follows whatever it says the next day. So say if this night, the polymer transient factory say, hey, I discovered something. And then the next morning, everybody will point their lens to that thing and measure whatever they can. So that's pretty fascinating. So I think we had more recently is the materials project. I think there will be somebody coming and talk about that in much detail, so I'm going to skip it. This is very related to what Timur is doing, and it's a web-based or cloud with some cloud concept on it. But a small project with over 5,000 users, just using this single thing. So 5,000 in science domain is a large number. So just so you know, we're not aiming millions. So this is the past. So what about now, right? So now what we are seeing is more data and new challenges. So we literally have new projects coming in, either old projects or new projects, saying that, hey, we have more and more data, we just don't know what to do with it. So what do we do about it? Just to prove it, right? So we do have some examples about that. So I'm just listing a couple of the very high profile ones. So if this works, the people will get a Nobel Prize. In this case, again, right, for the second time. But anyways, so this is this is trying to study the cosmology, the basic theory of cosmology, how the universe is born and how it evolves in a very fundamental level. It involves two things. One is a huge telescope taking a lot of pictures. So they need to analyze the petabytes and petabytes of data in the pictures. And at the same time, they can't draw any meaningful conclusion with the pictures itself only. So they have to run millions and millions of simulations as well, simulating the universe, and then do merge the data together and do statistics so that they draw a conclusion. So this involves not only big computing, but also big extreme scale data analytics. So there's a problem from every stage: generation, transportation, storage, analysis, iterative analysis, things like that. All right, so another astronomy. So this thing already won the Nobel Prize once. I'm not sure they can win another time, but so they're trying to figure out what the cosmic wave background is. So a lot of these things have a common, a lot of the fundamental science things have a common characteristic, which is they need to do experiments, and they also at the same time need to do simulation. So, and combine the result of the two, they can draw the conclusion. Otherwise, they won't make much sense. So, how we are dealing with the data problem and the traditional HPC problem now. So right now, what we are doing is we have two classes of systems at NERSC. So right now we have Hopper, which is 1 petaflop, Edison, which is 3 years newer. So we normally get a new machine every 3 years. 3 years newer, it's about 2 point something petaflops. And they are very good at doing computing intensive work. Say if you run one simulation on 100,000 cores. And we have another class of machines that's normally funded by the community. So these are funded by DOE directly. So funded by the community, we have more traditional like clusters, that's IBM one, doing all kinds of different other things like high energy physics, the finding Higgs boson thing was done here, and a lot of genome sequencing. So we have been using two different classes of machines to do the two different classes of jobs. But when the challenge become more and more, and you can't really separate the simulation part from the data part, or the data part from the simulation part. So we need to find some other solution to tackle the problem. So, so we went into this class of users and asked them, hey, what do you like about this? Why can't you just run it here, right? So here are some of their requirements to run. For example, I want to implement very complicated workflows, right? Or we want flexible policies. You know those big machines has very strict policies like what you can run, what you can't, right? So, and you want local disk. So this is very counterintuitive that almost all the supercomputers has no disk on any of them, right? So this, but comparing to the industry, everything is a share nothing design. Everything has local disk. So, and or very large memory, or massively serial jobs. This, I mean, in the traditional way, normally people run one job with 100,000 cores. 100,000 is like a pretty big number. So in this case, I also want to use 100,000 cores, but I want to run 100,000 small jobs. So this will break everything on the big machines. So you just can't schedule it. And also, the network communication going outside and inside is very important. So we do want to enable all the compute nodes on the supercomputer to talk to the outside, but in the same time, we don't want our computers to become the largest spammer in the world, right? So it can do a lot of spamming if you want to, and some other things. So one key point is that a lot of them are not hardware related. So that's why we think we found a solution that can serve both purposes in one system. So that's why after some study, we just announced Cori, our next machine. So basically, we name our machines after dead scientists, right? So got Hopper, Edison. The previous one was Franklin, and then was Bassi, Gicard, whatever. So this one is Cori, named after a biologist, the first female Nobel Prize winner in America. Yeah. So this is going to be a combination system also from Cray. So we will have 50 cabinets of Knight's Landing. If you don't know, if you know what Xeon Phi is, so it's a very heated topic in the industry now. So, right. So Xeon Phi is right now is offload mode. You have PCIe card that goes into your motherboard, and then you run some code on your host and offload something to Xeon Phi and come back. So Knight's Landing will get rid of the CPU and make the massively parallel used to be the assistant GPU and promoted to the real CPU. So we have 50 cabinets. 50 cabinets about 10,000 nodes. So if you do the counting, and then at the same time, so this is the Knight's Landings are primarily targeted at the highly parallel massive computing simulation jobs. So at the same time, we are also getting 10 cabinets of Haswell compute nodes. Haswell is the thing after Broadwell, I guess, whichever came first. And so it's Sandy Bridge, Ivy Bridge, Broadwell, Haswell, or Haswell, Broadwell. So which will have a much larger memory, which will be more suited to run the data-intensive workload, including the popular data analytic frameworks like Hadoop, Spark, SciDB, blah, blah, whatever. So, and then another interesting thing, because there's still no local disk in any of those, right? But we do want local disk-like performance and features. So that's why we're getting another 4 cabinets. We call it the burst buffer. Basically, it's several racks of solid-state drives. It's going to be expensive, and somehow logically, every node will somehow see part of the SSDs and use it as local drive. And of course, one of the points that we're getting Craze is that they have a very fast interconnect, which is different from InfiniBand or anything. And they can run very reliable, very high performance, low latency, high bandwidth communications so that our simulation will run very efficiently. And in addition to that, we have about 30 petabyte of disk running at about 432 gigabyte per second peak performance. So actually, if we put a number here, pretty much we have to make it before we can accept the machine. So it's a real number. It's not a theoretical peak or something. So, and the burst buffer is expected to have about 2 terabyte per second. So yeah, 2 terabyte per second is pretty big. And we're expected to have the first part of the machine, which is the phase 1, the Haswell part, sometime in 2015, and the rest of it in 16. So that's so just for completeness. So this is the design graph of the Cori system. And of course, now we have the hardware. How about the other part? So if you only have the hardware, you can't do anything. So that's why we have a group called Data Analytics Services Group. We basically do 2 things. We engage with science teams, so to try to help them to solve real science problems, try to help them to develop a system or help them to use NERSC to do their data analysis. So am I out of time? No, yeah, 1 more minute.
It's a warning.
Okay. So, and during the process, we try to discover some common patterns so that we can find out what services we want to deploy so that it can serve a broader community. So another task of the group is that we provide production data services. We have a pipeline that can bring a product from inception to deployment to retirement efficiently. So if you can recognize these icons, so all of these are at some stage in the pipe right now. So, oh, by the way, if you can recognize all of them, let me know. I'll give you a prize. So anyways, the message is, so I'm trying to conclude now. So the message is, we are a computing center for open science, and we have a lot of cool stuff and a lot of cool projects going on. And if you're doing open science, or if you have a project, or if you have a product you're looking for customers, maybe we should talk. So we may have a surprise for you. All right, thank you.